We're going to want our learning algorithms to return optimal policies.
Right.
But to do that, we're going to have to say what we mean by optimal. So I know we talked about this in the context of MDPs, but I thought it might be worth revisiting just to see that there's different choices we could make, and the choices that we make have implications about what it means to be optimal.
Okay.
So here's in particular what I want to get at. The notion that, let's say we have some particular policy that we're going to follow. By following that policy from some initial state, we're going to have a sequence of states, actions, and rewards. But there's actually multiple possible sequences of state, actions, and rewards that can happen because the domains are stochastic.
Right, right.
So let's say that we've got some particular policy that we want to evaluate, and it generates this kind of sequence of states with this probability, and this kind of sequence of states with this probability, and this kind of sequence of states with this probability. How do we turn all that possibilities into a single number so that we can say, oh, this policy is this good, has this value, and the other one is a smaller value, so I like this one better. All right? So here's the 4 steps that we need to do to take what was once a sequence of sequences or a set of sequences of states and turn them into a single number. So the first step is for each of the state transitions, we need to turn it into actual numbers, the immediate rewards.
Sure.
So in this case, maybe landing in a red state gets us minus 0.2 and landing in a green state gets us a positive 1. What is it in the definition of the MDP that allows us to translate between state transitions from some state via some action to some next state to actual values, actual numbers for that transition?
Oh, it's our reward function.
Exactly. That basically just gives us strings of numbers, right? So what was strings of states now becomes strings of numbers. And those are infinitely long, right? Because this process can continue in an unbounded way. If we're talking about the infinite horizon, we just leave it that way. But if we're talking about some kind of finite horizon, like, I don't know, say truncating it at 5 steps, we can actually take the sequence of numbers that results and cut it off after just 5 transitions.
Mm-hmm.
Now, we need to take that list of truncated numbers and for each of the sequences, turn it into a single number for that sequence. It's called the return for the sequence. So how do we do that? Yeah. Often what we'll do is actually add them according to some kind of discount factor.
Mm-hmm.
If r sub I is the reward that we got on step I of the sequence, we might want to actually sum up the discounted rewards.
Right, and my recollection is that that's a geometric sequence, so it allows us to do infinite sequences in finite time, or at least infinite numbers and make it a finite number, so to speak.
That's right. Yeah, no, and so that's a good point, actually, because we might be doing this finite or we might be doing this infinite. In general, we do it up to the length of the horizon.
Mm-hmm.
All right, and so let's just say for concreteness, you could imagine having a discount factor of 0.8, and that gives us a way of summing up the numbers that have been generated by these states and getting a single number for each sequence. And then finally, we have to take those multiple numbers, one number for each of the sequences, and turn it into a single number that summarizes across all of them.
I see. So you would just average them according to how likely the sequences are.
Good. So it's also taking the expectation. All right, and so I've annotated these sequences with their probability. So what you should be able to do at this point is actually, according to these parameters that I filled in, say what the value of this policy is, assuming that these are the 3 possible trajectories that could result. What is the single number that actually summarizes this, the output, the outcomes of this policy?
Right, and so that's when we talked about MDPs is long-term expected reward.
That's right, or value or utility.
Mm-hmm.
All right, so can you work out what it is for this case? We're going to make that a quiz.
Oh, okay. Let's pretend. Oh, wait, I've got one more thing. I think I know what the answer is, but just to force you to be, absolutely concrete. I know what happens when you hit a red circle. I know what happens when you hit a green circle. What happens when you hit a white circle?
Good question. They look like zeros. Let's just make them zeros. So they're not going to come into play except for the fact that they're 0.
I like it.
All right. So you should be able to reduce this entire sequence to a single number, and you can put the number in the box.
All right. Sounds good. Let's do it. Go.